Hello and welcome back. In this video, I want to talk about continuous random variables. So remember, the random variables are the variables or quantity whose possible outcomes we are contemplating and trying to come up with a distribution thereof. So before we had random variable, which would be the outcome of a student score. And that was the random variable. Those were discrete in the example I gave before. So we had things like for a discrete random variable indexed by the label I, some integer. Then we would say things like the average value of some quantity would be, well, you would sum over all possible outcomes of the values of the random variable, the probability of each outcome. Oh, take it back. I think I wrote it slightly differently, so I'll go back. Pi times the value of this thing I'm averaging evaluated on random variable I. And we had things like the standard deviation in F would be the standard deviation squared is easier to write down here, is the average of F minus its average squared. So to get the standard deviation, you have to take the square root of that. So writing it out, it would be sum over I Pi times Fi minus the average value of F, which is just a constant, squared. So this is how we calculated expectation values or average values and standard deviations in the last couple of videos. All we're going to do is just generalize this slightly and extend these definitions to cover continuous variables. Now, so let's imagine I have a continuous random variable. And let's call it X, okay? And X's label all possible outcomes, and we're going to assume that there's a continuous distribution of them. So if there's some quantity, I'll just kind of F, just borrowing from before, I'm going to extend the previous definition by just passing from a sum to an integral. So instead of being sum over I, it's going to be integral over X's, F of X times the probability of each outcome X integrated over all possible outcomes. And that's the natural generalization of the discrete definition. The standard deviation then would simply be given by the integral of the probability of X times F of X minus the average value of F, and then I have to square that quantity dx. And you'll see that's the natural generalization of this definition. One comment, I should have said that before, excuse me, before we had the sum of all probabilities had to be 1. Now what we have is that just naturally extends to the integral of all probabilities, which are now functions, continuous functions of X, dx must be 1. So that's really, you're just replacing sums with integrals in a more or less obvious fashion. All right, let's do an example. Okay, let's imagine that we have radioactivity. Okay, and what we have is a probability describing the probability. I have to say this the right way. We could say this as a survival probability. So this is or I tell you, all right, so the probability, I'm going to call it P. I'm not going to use X now. I'm going to say the random variable is T, time. And that's going to be some constant times e to the minus lambda times t. And the idea is in time t to t plus dt, there is a probability of decay equals P of t. So P of t tells you what's the probability that a little unstable element explodes in the time window t to t plus dt. All right. Now, so that's the interpretation of it. A typical thing we want to do then is figure out what is this constant c. So to do that, and usually this is how it works, the overall coefficient for the probability distribution can be set by requiring that 1 equals the integral of P of t dt. Now let's be a little bit more careful here. What about the limits of integration? Well, assuming that I start, I'm going to assume that I have something at the beginning. So that means the decay can only happen in the future. So I'm going to start at 0. And what I'm saying is if I wait forever and a day, go all the way to the time equals infinity, there's a 100% probability that it will eventually decay. And that means I get the integral should be 1. So then when I plug in c e to the minus lambda t dt from 0 to infinity. Oh, I should also say lambda is also just a constant. What it does is kind of set the rate at which the decay can, the probability for a decay sort of fades away. Okay. This normalization condition becomes 1 equals c. Now the integral of e to the minus lambda t is minus 1 over lambda times e to the minus infinity minus e to the minus 0. And that's just going to be c over lambda, or turning it around, we learned that c equals lambda in order that all the probabilities add up to 1. Okay? So a lot of times distributions are quoted with an overall coefficient. By fixing the normalization, you can always relate that coefficient to the other parameters of the distribution. All right, so using that, I can rewrite P of t and say that that's lambda e to the minus lambda t. Okay, and then I could ask, what is the expectation value, the typical time, the average time that a decay occurs? So the average decay time Well, that would just go back to our definition for averages. That'd be the integral of t, the thing inside the bracket, times the probability, which is a function of t, dt, and again from 0 to infinity. That becomes lambda times the integral of t e to the minus lambda t dt. So you can integrate by parts and get this answer, or I can go back here and see that there's a trick. So we could do by parts, or use trick. And I'm going to use the trick because it's more fun. So there's a neat little trick here. Whenever I have this integral, e to the t, I'm sorry, integral t e to the minus lambda t dt from 0 to infinity, that's actually, I can think of this as a function of lambda. So call that I for integral. It's a function of lambda. And or actually, you know what? Take that back. I'm going to define this to be I. And look what happens. If I were to take d by d lambda with a minus sign on I of lambda, that gives me the integral that I want. Because the integral, as long as this is a smooth converging integral and a smooth integrand and all that kind of stuff, the integration and differentiation commute. But on the other hand, from the previous problem, that integral just equals 1 over lambda. So what I find is that this integral should be minus d by d lambda acting on 1 over lambda, which is equal to 1 over lambda squared. So coming back here, the expectation value of time is lambda times this integral, and I just said this integral equals 1 over lambda squared. So I learned that t equals lambda times the integral of t e to the minus lambda t dt equals 1 over lambda. So that's a kind of a curiosity that t, the average expectation value for t, also gives 1 over lambda, which is the normalization, the integral we had in the normalization constant. That's kind of an interesting little result. We can similarly find the standard deviation. Oh, so let's interpret that. Sorry, I should have said that. So the idea is, so here's a graph of t, p, and what we're finding is there's a curve here, exponential decay, and roughly you ask, when is it likely to decay? Well, it would accordingly be somewhere where t is about 1 over lambda. That'd be the average or expected decay time. And then we can see, we could also ask, well, okay, yeah, that might be the average, but how are things spread around it? Are things kind of tightly packed, or does it kind of linger for a long time? So the standard deviation for decay would be the quantity which measures the spread. So that would be sigma for decay. I'll actually compute sigma squared, and that would be the integral of the probability distribution. So that would be e to the minus lambda t times lambda multiplied by t minus the average value of t, which is 1 over lambda squared, dt. And we can kind of expand this out here. So this would become, this is actually going to be the same as doing the lambda integral e to the minus lambda t squared minus, or sorry, dt minus 1 over lambda squared. Going back to the last video where you could basically say that sigma squared is the average of f minus the average value of f quantity squared, but it also equals the average value of f squared minus the average value of f quantity squared. Oh, sorry, should be a minus sign. So I'm using the second version of that. And to do this integral, I'm going to write that as 2 derivatives with respect to lambda on the integral of e to the minus lambda t dt from 0 to infinity, which, so that's 2 derivatives because of 2 factors of time. The minus signs go away. That's 2 lambda derivatives acting on 1 over lambda, which equals minus 1 over lambda squared. And another one, so it'd be minus plus 2 over lambda cubed. Okay, so pulling that together, I would find that the standard deviation for the decay time, the spread in the decay time, equals lambda times that integral, which gives me 2 over lambda cubed minus the average value squared, which is 1 over lambda squared, which equals 1 over lambda squared. 2 over lambda squared minus 1 over lambda squared gives me that. Therefore, sigma for decay, standard deviation in the decay time, is 1 over lambda. The fact that all of these integrals keep giving me 1 over lambda is really just an artifact of the simple nature of the exponential. Other distributions won't have that property. Okay, so this is an example. Basically what this is saying is if 1 over lambda is the width is the average value, we see that the width of kind of the typical spread is roughly on either side about the same. So most of the particles will decay in this window. And once you get beyond that, things start to fade off pretty quickly. All right. There's another example of a distribution, which is really useful. It's the Gaussian distribution. Or, no, this is the Gaussian probability distribution. Or you might have heard of the bell curve. Okay, it's probably the most important continuous distribution that we have. And that's given with one random variable. It's given by some constant times e to the minus, I'm just going to call this a times x squared. So that is the Gaussian probability distribution. It's an exponential with an x squared in it, multiplied by some normalization constant, as usual. This is a tricky one. Exponential integrals are easy to do. We can do those piece of cake. Maybe we integrate by parts. Gaussian integrals are much trickier. I'm really just going to give you the answer to that one. You can look at it. You can use Mathematica or any other tool to find this. If you really are interested, I can show you how to do it. There are different ways, but there's a standard trick for doing this. All right. So I will just tell you the following result. It turns out that the integral from minus infinity to infinity of e to the minus ax squared dx equals the square root of pi divided by a. I'm not going to justify that. I'm just claiming without proof. You can confirm it using various tools or an integral table. All right. But if that's true, we immediately conclude that if these are probabilities distributed from minus infinity to plus infinity, that the coefficient c must equal square root of a over pi, so that this thing integrates to 1 when you account, say that when you add up all probabilities, you get 1. So my Gaussian distribution, P, is now the square root of a over pi times the integral dx from minus infinity, sorry, take it back, times e to the minus a x squared. And I'm going to, when I take averages, I integrate from minus infinity to plus infinity. If you're thinking about the shape of this, it looks something like this. 0 mostly, and then it kind of bumps up symmetrically, and it fades off to 0. It's just like a hill. The average value clearly is going to be 0, just because it's symmetric around that. Or this probability distribution is an even function, so the expectation value of any odd power of x will be 0. What about the standard deviation? What's the width of this? So that's simply going to be the average value of x squared minus the average value of x squared, which we just said that that was 0. So to do this, well, okay, what would that be? That would be the square root of a over pi times the integral of x squared e to the minus a x squared dx from minus infinity to infinity. Now this integral is hard. In fact, I know of no honest way to do it. Maybe there is one, but I don't know it. Instead, though, I can use that differentiation trick that I had before, which is actually why I showed it to you then. And I see that if I define an integral called I, it's a function of a, which is the integral of e to the minus a x squared dx from minus infinity to infinity, then if I were to take minus d by dA acting on I of a, that would simply give me x squared e to the minus ax squared, because this is, I mean, yes, the integral's hard, but that's just a nice lumpy smooth function. It's certainly the integral is going to converge. So the derivative and integration should commute, and that's exactly what you get. If you take minus the derivative with respect to a, you get a factor of x squared out front. On the other hand, and this is the thing I need, right? This is the integral that we're trying to calculate. On the other hand, this integral, the first integral, is nothing other than the square root of pi over a. So what we have to do, we get the result that x squared e to the minus ax squared dx is a minus the derivative with respect to a acting on square root of pi over a. And that is going to give me square root of pi. The minus signs go away. I get a factor of a half, and I get a to the 3/2 downstairs, or I could write that as half root pi over a times 1 over a, just doing some algebra. They're equal. The reason I write it this way is so that I can compare it here, and this prefactor will cancel. And what I get is that the standard deviation for a Gaussian random variable, x, centered on 0, is going, the standard deviation squared is going to be 1/2 from here. This factor cancels with the normalization constant, and I get 1 over a. Or the standard deviation is 1 over the square root of 2a. Now, what does that mean? What that means is that in this distribution, the height of the distribution equals square root of a over pi. Right? That comes simply from looking at this when you plug in, sorry, not there. This part right here. If you plug in x equals 0 at the peak, you just get a over pi. So the bigger a is, the taller the Gaussian distribution is. So if a is large, this becomes very high, spikes way up. On the other hand, what is the typical width? And well, the typical width, so you'd have plus sigma, and on this side you have minus sigma. And sigma is 1 over square root of 2a. So that means if a is large, then it starts to look like a very narrow spike for large a. And for small a, it's very shallow. And that kind of makes sense because if all the probabilities have to add up to 1, if it's very wide, it has to be short, and if it's very tall, it has to be narrow. And that's how you can interpret those. All right. There's one last little comment I want to throw out, which is really useful. And I should have said this way back, but I forgot to, so I'm going to throw it in here. And this is to look at relative likelihoods or relative numbers. So this would mean, well, let's just take the example of x here. And let's say we wanted to know what is the relative number of times that we get x equals, say, 1 compared to x equals 2, for the Gaussian distribution. Well, remember, well, I can divide by the total number of outcomes, which in this case might formally be infinite, but formally we'll proceed because we're brave. So I just just divided top and bottom by the same thing, and I recognize that the relative number of times that something occurs is nothing other than the ratio of the probabilities. Now, when would you maybe use this? Well, the number of times that something happens, that's kind of like a ratio of density. So you could be saying, okay, in this room, there are many possible heights for a gas molecule. Let's compare the number of molecules at the top of the room to the bottom of the room. And what you'd want to do then is take the ratios of the probabilities to get those numbers. Okay, that's a handy little fact. Or so more generally, any other two numbers, you would do the ratio of x, the number of times x occurs compared to the number of times y occurs, is simply going to be the probability of x divided by the probability of y for any x involved. Okay, so that was something I should have thrown in when we were looking at discrete random variables. I just forgot to. It doesn't really make sense to put it here, but I wanted to get it out there somewhere. Okay, so that ends our little lightning lesson on probability. I want to use these ideas now to discuss an ideal gas and learn what temperature is. So I'll catch you next time. Thanks.